In this video, we will learn about pericyclic reactions. Pericyclic reactions are a little bit different in how they work compared to the ionic type of reactions we've talked so far, and of course radical reactions as well. So in a pericyclic reaction, the distinguishing feature is that it's a concerted process, so it all happens in one step, and the transition state for the process has a very cyclic nature to it. There's no kind of electron sink or electron source. There's no overall flow of charge from one place to another. Everything is kind of contained into a single cyclic transition state. So if we look at this in terms of this example here, this is an example of an electrocyclic reaction, which is a subclass of pericyclic reactions. The mechanisms for these reactions will be nice and simple. They go through just these circular type of arrows here because we have a single transition state in which all of that is happening at once. This kind of should remind you of benzene rings aromaticity, in the end getting you to this product here. A question that often comes up is, well, does it matter which way these arrows go? And no, it doesn't, because in the transition state, the molecule doesn't think about this in terms of arrows. It creates just a single cycle of shared electron density. These arrows are more for us to try to conceptualize things, so you can draw it counterclockwise or clockwise. And so that may feel like it's simple and that there's not much analysis needed, but it turns out there's a lot more stereochemical aspects that come out during these reactions, and the way we will understand those is to do some what's called frontier molecular orbital analysis. What we're doing here is looking at the molecular orbitals, specifically the HOMO and the LUMO, and more specifically the pi HOMO and the pi LUMO. And so it's probably worth spending just a moment here to review those concepts. So the way that we're going to think about our pi molecular orbitals is we're going to create them using the linear combination of atomic orbitals, where we're taking all the different p orbitals on these atoms and mixing them together. So if you put in 4 atomic orbitals, you'll get 4 molecular orbitals out. And we do this in a way that's guided in the end by math, but we're not going to do the math here. So our rules are basically that we're trying to maintain symmetry, kind of a left to right symmetry, and we're also going to be minimizing nodes, or maybe better stated, we're going to have our lowest energy pi molecular orbitals be the ones with the least nodes. And so the way this works is I've given you the empty atomic p orbitals here on each of these atoms. So for just a molecule of ethene, there's 2 ways to organize your phasings. So either they can be aligned with each other, in which case there is no vertical node between the p orbitals, or they can be aligned against each other, in which case there is a node between the p orbitals because your phasing goes from, I guess, black to white or positive to negative. I think a point of confusion for students will be, well, is this symmetric from left to right? And it's not symmetric in terms of a plane, but it's symmetric in terms of what's called inversion. So you can kind of imagine a point up here being the same as the point down here if I kind of go through the middle. So the same process for the butadiene over here. It gets you to a similar beginning where everything is aligned, and a similar end where everything is opposed. And in the middle, we can come up with orbitals that look like this. This is not something you have to commit to memory. There's all sorts of summaries of these for different numbers of atoms and pi bonds and electrons. So that's just the empty molecular orbitals for both of these molecules. And we just have to remember that what we want to always do is to fill in our electrons. So here for this pi bond, I'm trying to explain this pi bond using this frontier molecular orbital diagram. And I'm going to have 2 pi electrons that are associated with those pi molecular orbitals. So I should be drawing in just the 2 electrons like so. For butadiene here, now I have 2 plus 2 is 4 total pi electrons, right? 2 for each pi bond here. So when I fill in my electrons, I should find out that that's what the filled molecular orbital diagram looks like. And in the end, what I really care about is that these 2 are the HOMOs for their respective molecules, and these 2 are the LUMOs for their respective molecules. Something really important when it comes to pericyclic reactions is that the HOMO and the LUMO of a molecule is not static. It's not a permanent feature of the molecule. It turns out we can change which is the lowest unoccupied and which is the highest occupied molecular orbital. The way this is done is to promote electrons by adding energy to a system. So in the ground state of butadiene, that's the lowest energy state, we'll have our electrons like so, which we just saw in the previous slide. But if we add in the correct amount of energy to the system in the form of UV light, that UV light has to have energy matching this energy gap right here in order to get an electron to be promoted up a level. And so if you recall from general chemistry, that's related to the quantization of light and energy, and you could figure out all of that from wavelength and E equals h nu. For our diagrams, what we care about is that by promoting an electron, what we then create is an excited state of our molecule, indicated often by a star. And in that excited state, what used to be our LUMO in the ground state is now our HOMO, and what used to be the LUMO plus 1 is now the LUMO in the excited state. And so the point is, by exciting our molecule, we can change which molecular orbitals are reacting in a pericyclic reaction. Just in case, here's another example. So here I'm going from a cyclohexene pi system here, which is just 2 carbons with a pi bond between them. So really this is the pi molecular orbital that I'm going to be dealing with. Upon excitation, I'm going to get 2 here and here. And you'll notice in this case I don't have a unoccupied molecular orbital, or at least a pi molecular orbital, and that's okay here. So why do all these frontier molecular orbitals matter? Well, it turns out that the outcome of a pericyclic reaction is dictated by the reaction conditions and by the number of electrons in the pi system. And the reaction conditions can be either thermal or photochemical. If you're thermal, then you'd be in your ground state. If you're photochemical, you'd be in the excited state, and that could lead to a different outcome. So let's look at this example again here, where I've pointed out the 2 carbons where the reaction is happening. So really we only care about what the phasings of our orbitals are, really the atomic orbitals that make up the molecular orbital. We care about the phasings just at these ends here. And what that might look like is like so, where I've left out those middle 4 carbon p phasings just because we don't really care about them for the reaction. So again, we are reacting at these end carbons. And if you're looking at this, there's 2 ways to make bonds to those end carbons. One of these is what's called suprafacial. In other words, if both of my bonds were formed from above the plane of that molecule. And the other way is to do what's called an anterofacial process, in which now on one end I'm forming the bond from above, and on the other end I'm forming the bond from below. So what we're thinking is that a given pi system can react in a suprafacial way, so its ends react both on one side, or it can react in an anterofacial way. One of its ends reacts on one face, the other end reacts on the other face. Why does this matter? Well, depending on how you do your reaction, that can lead to different stereochemistries. And if you think about anterofacial versus suprafacial, it's probably easier to do a reaction suprafacial because you can just have your 2 molecules meet together face to face rather than trying to twist your molecules around to be able to get to this anterofacial combination or mixing of orbitals. All of this is rooted in some very complicated math that we're not going to even come close to thinking about. But it turns out that these can be really nicely summarized in what are called the Woodward-Hoffman selection rules. Each different type of pericyclic reaction has a slightly different version of these selection rules, but they are all going to be rooted in the number of electrons and the reaction conditions that are involved in your reaction. Real quick, we'll go over the 4 common types of pericyclic reactions that we'll cover. There are other ones, but these are the 4 most common ones. So the first one that we'll talk about is a cycloaddition. And in this type of a reaction, we have 2 pi systems reacting together to create a new ring. When I say that we can do a pericyclic reaction in one direction, that's always leaving open the fact that you can do the pericyclic reaction in the other direction. So here we would call it a cycloreversion. So in my example, I have a cycloaddition going from left to right. And if we were to do the cycloreversion, we would go from right to left. In every cycloaddition, we have these two pi systems. They don't have to be two separate molecules, but they do have to be two separate pi systems. In every cycloaddition reaction, our net result in terms of bonds formed and broken is going to be 2 pi bonds lost, 2 sigma bonds gained. And so you can kind of see that because we have 3 pi bonds here and only 1 here. And we have those 2 new sigma bonds made right here and right here. The next type of pericyclic reaction we'll talk about is an electrocyclic process. So we can have electrocyclic ring closings or electrocyclic ring openings. And in this case, we're always dealing with a single pi system, either a linear pi system that's closing up into a ring or a ring that's opening up into a linear pi system. And so here's an example of that happening. Overall, we'll see that we have a net of +1 sigma bond and a loss of 1 pi bond. The next type of pericyclic reaction is the Sigmatropic reaction. These are also known as rearrangement reactions. In this reaction, what I think of happening is that a sigma bond is broken and a new sigma bond is made. So it's like the sigma bond has changed places. In this example here, what I'm seeing is that the carbon-hydrogen sigma bond is there in the reactant. We're breaking that sigma bond, and then we're creating a new carbon-hydrogen sigma bond. Overall, there's no net change in the number of sigma or pi bonds. Finally, there's a similar looking ene reaction. In this reaction, we have kind of a combination of a sigmatropic reaction and a cycloaddition reaction. So what we'll have is a pi system reacting with another pi system, but more specifically, an allylic atom on that pi system. So commonly, that's going to be an allylic hydrogen. So in this reaction, we are going to be overall gaining a sigma bond and losing a pi bond. And we are kind of combining these two pi systems into a single one, but you can think of it as not a cycloaddition because there's this sigma bond that's in between here. So in a cycloaddition, this would have been a pi bond. Here, it's a sigma bond. So that was a quick look at pericyclic reactions. We did a little introduction to how pericyclic reactions work, that we care about the pi molecular orbitals, and specifically the ends of those pi molecular orbitals, and that they react together in either supra or anterofacial ways, following a set of Woodward-Hoffman selection rules. We haven't talked about how those rules apply specifically to these 4 reactions that I just mentioned here, but we'll do that in the future.